All right, now we're ready to talk about special types of vector transformations that are called linear transformations. These are linear transformations are exactly the transformations that are going to have all the nice properties that we've come to expect about all the stuff that we're going to talk about in linear algebra. And so a linear transformation, we actually went over this. I went over the definition in class. This was our last class before our in-class course turned into an online course. But the last class that we were at, I talked about the definition of a linear transformation. And so a linear transformation is going to have a few properties. We're going to let T be a transformation, or just remember that just as a fancy word for a function, from some vector space V to W. I want to be careful about our notation here. I want to say T colon V to W. That's the notation that T is going to be a transformation from V to W. But this transformation is going to be, this is a linear transformation if it has the following properties. So this is a linear transformation if it has the following properties. One is what's called additivity. So if whenever I take two vectors, u and v, this is the same as plugging in t of u plus t of v. And I want this to hold for all vectors, u and v, in our domain. That's the first property, so that's called additivity. In fact, let me write that. This is called additivity. And then the second property is called homogeneity. And the idea here is that I'm going to pick some vector from V, and I'm going to pick some scalar. Remember, for us, that means real number, because all of our vector spaces that we've talked about are real vector spaces. And T of CV is going to be the same as C times T of V. And I want that to be true, again, for all vectors V and V, and for all scalars C. Okay, so again, that's called homogeneity. So if we have both of those criteria, then our vector transformation is going to be called a linear transformation. Okay, that's the big definition. So what I want to do is I want to look at a few linear transformations, or rather I want to look at a few vector transformations and determine whether or not they're linear. Before I do that, I just want to add one other equivalent definition. Okay, so if I combine both of these properties of additivity and homogeneity, equivalently T going from V to W is a linear transformation if it has the following properties. So you can actually just combine these properties into one. So if T of Cu plus dV is C T of U plus D T of V. And again, I want this to be true for all vectors U and V, and for all scalars C and D. So sometimes it's convenient just to think of this as a single property. That really means that we only have one thing that we have to check rather than two. But they're completely equivalent. So I'll probably bounce back and forth between the definitions there. All right, so what I want to do is I want to look at an example. And for now, I want to just pick both V and W. I want to pick our domain and our codomain to both be R2, because this is going to give us a decent bit of intuition as to how linear transformations work. Okay, and why they have the properties that they do and all that. So as we talked about in class, I want to kind of go through and I want to re-explain everything that we've talked about in class in the context of abstractly and formally working with a linear transformation. So let's start with something completely, let's start with a completely explicit linear transformation. So I want to just completely write it down and then we'll talk about it. T of xy is going to be 4x plus 3y and x minus 2y. Okay, so that's how we're going to define a vector from R2 to R2. Notice that our input is a vector in R2 because we have an x and a y. And our output also is a vector in R2 because there's two components, right? We have a first component and the second component. The first component and second component. So this is going to be a map that takes R2 to R2. And what I want to do is I want to think about all the stuff that we know about these functions. So first, let's prove that t is linear. After that, what I want to do is I want to determine where we're pretty familiar with R2 at this point. R2, remember, comes with a standard basis. So a standard basis of I and j. So that's the vector 1, 0, and 0, 1. I want to think about where those standard basis vectors get transformed to under this transformation. So I want to think about if I plug in 1, 0, and 0, 1, what happens? Right? What are our outputs for those vectors? So I want to determine t of 1, 0, t of 0, 1. And then I also just want to emphasize, this is again a point that I've made in class, is I want to emphasize that if you know these output vectors, t of 1, 0 and t of 0, 1, then you know everything. Okay, every possible value can be written if we know what those two output vectors are. So let's find. I'm going to find t of, say, 2, 3 in two ways. I'll explain what that means when we get to it. So first things first, let's prove that t is linear. So what we need to do is we need to prove that it has that it follows those two properties that we talked about. I'm just going to prove the two properties separately for now, for the first time. Once we get used to proving those properties, we'll go through and we'll use our equivalent definition of linearity. So for now, let's just prove, let's say I have t of some vector plus some other vector. So our vector is going to be xy, and the second vector will be x prime, y prime. And what I want to do is I want to look at what is that going to be. And I want to make sure, is that going to be t of xy plus t of x prime, y prime. I want those to be the same. That's what I'm hoping for. If they're not the same, this is not linear. Okay, if they are the same, it is linear. So that's what we need. So we need to compute both of these. The right side is arguably easier to compute. So the right side is going to be t of xy. We can just literally copy what we have here. T of xy is going to be 4x plus 3y, then the second entry is x minus 2y. X prime, y prime is going to be 4x prime plus 3y prime. And then the second entry will be x prime minus 2y prime. Okay. And what we're going to do is on the left side, I'm going to take the two vectors that are inside our linear transformation and I'm going to add them up. This is x plus x prime, y plus y prime. And so what we need to do is we need to think about where do x plus x prime and y plus y prime get put into our transformation. So if I were to replace the top value with x plus x prime, what we would get is our output is going to be 4 times the top value plus 3 times the bottom value. And then the bottom value will be the top entry, x plus x prime, minus 2 times the quantity, minus 2 times the bottom entry, so that's y plus y prime. Okay, so that's where, that's the image of our pre-image, x plus x prime, y plus y prime. And on the right, what we have is we have two vectors in R2 being added up. So this is going to be 4x plus 3y plus 4x prime plus 3y prime, x minus 2y plus x prime minus 2y prime. And so now what we're going to do is we're going to look at really what we wanted to know, and I should have written this slightly better. I really should have written this a little bit better, but we wanted to know, are these equal? And so the answer is yes, they are equal, right? If you expand, if you were to distribute, say this top row, you got 4x plus 4x prime plus 3y plus 3y prime, and that's exactly what we have. Okay, written in a different order, but we know that the order doesn't matter that we write it in. And so then what we're going to do next is we're going to look at t of c times some vector. Okay, so we just established that this linear transformation is additive. Now we need to check whether or not it's homogeneous. And so what we're going to do is we're going to look at t of, if I were to take the c and multiply through, we would get cx, cy. Because we know when we take a vector and multiply through, that's how it works in R2. And so this is going to be, now we're going to think about what's our image if we take cx, cy and put it into our transformation. And so the rule is going to be the same. We're going to get 4 times our top value. So 4 times cx plus 3 times our bottom value. And then that's our top entry. And then on the bottom, we're going to end up with the top entry minus 2 times the bottom entry. And there we go. So that's t of c xy. And I just want you to notice, let me just write this a little bit better here. I want you to notice that this is, you could actually factor a c out of the top and bottom. This is c times 4x plus 3 and c times x minus 2y. And then you could actually factor out that c, and this is the same as c times 4x plus 3y, x minus 2y. And that's, of course, c times t of xy. Okay, so t is homogeneous as well. Okay, and since it's additive, so since this is additive and homogeneous, we can conclude that t is linear. Okay, so that's how that works.